As explained in our previous video, SE Plus addresses the vulnerabilities of the weighted least square state estimator by dividing measurements into two groups, the basis set, ZB, and the redundant set, ZR. The ZB contains the minimum number of measurements needed to solve the entire system equal to the number of variables. Although there are many possible basis sets, each can solve the system. In the SE Plus process, an error-free measurement from ZR replaces a bad measurement in ZB, progressively cleaning the ZB set. As a result, the voltage solution from ZB becomes more accurate, and the number of large residuals in ZR decreases. SE Plus stops when these large residuals are minimized, ensuring a solution whenever the system is observable. The weighted least square, WLS, state estimator was not designed to handle bad data in power systems. Even after 50 years, no widely accepted bad data detection algorithm exists for WLS. SE Plus uses a different approach by rejecting bad data-related measurements instead of detecting them. The WLS state estimator causes biased voltage estimates because it forces bad measurements to have small residuals, leading to biased voltages. SE Plus avoids this by dividing measurements into a basis set and a redundant set. SE Plus gradually replaces bad measurements in the basis set with error-free ones from the redundant set, resulting in a more accurate voltage estimate while isolating bad measurements in the redundant set, preventing them from affecting the estimate. A topology error occurs when a branch's state is modeled incorrectly, either from open to close or close to open. This makes the injection measurements at the branch's terminals bad. To avoid this, SE Plus tries to reject these injection measurements from entering the basis set, ZB, ensuring the state estimation solution is not affected by the topology error. To test the topology error rejection capability, we used a real case provided by a power company from North America, which has 3,409 buses and 4,228 branches. The measurement redundancy ratio is 1.93. In the test, a topology error is expected not to make the system unobservable, and the real power line flow on the branch must exceed 100 megawatt to test SE Plus's rejection capability on significant topology errors. We created topology errors on 10 branches, 5 from close to open and 5 from open to close, resulting in 34 bus injection measurements, real and reactive power, becoming bad due to these errors. Among these 34 injection measurements, we found 28 injection measurements are in the basis set ZB before we set up these 10 topology errors. The measurements in the basis set ZB are indicated by red color. After these 10 topology errors were set up, we run SE Plus and found that all injection measurements were rejected from the basis set except 8 injection measurements. The topology error rejection rate is 71.4%. The influence of these 10 topology errors was controlled by SE Plus, and the total absolute value of voltage residuals was changed from 13.54 per unit to 13.63 per unit, and the percentage of the influence is 0.67%. There is a topology error on branch 534 whose correct status is out of service, from bus 749 to bus 699. Injection measurements, our buses 749 and 699 were not rejected by SE Plus. The reason is that these two injection measurements formed a critical pair. If both of them were rejected from the basis, set ZB, the entire system cannot be solved. Now, let us investigate the influence of parameter errors on the solution of SE Plus. If a branch has parameter error, all measurements associated to this branch will become bad measurements. These measurements include the line flow measurements on this branch and the injection measurements at both terminals of this branch. The same real case provided by a power company from North America was used in this test. The measurement redundancy ratio is 1.93. We set up parameter errors on 10 branches by adding 0.25 per unit on the reactance X of these branches. In order to test the rejection capability of SE Plus on severe parameter errors, we selected 10 branches whose real power line flow is larger than 100 megawatt. We found 66 measurements became bad measurements due to these 10 parameter errors, and 28 out of 66 were in the basis set ZB before we run SE Plus, which are indicated by red color. Then we run SE Plus and found 26 out of 28 measurements were rejected by SE Plus. However, 4 measurements, originally not in the basis set ZB, entered ZB. So totally 22 measurements were rejected by SE Plus. The rejection rate of parameter errors is 78.6%, and the voltage magnitude residual changed from 13.54 to 13.83 per unit. The rate is 2.1%. In order to thoroughly test the bad data rejection capability of SE+, we have conducted massive and random testing on a big power system which has 136.59 buses. We choose 113.659 bus system for this test is because it is big enough to allow different random selections of 500 topology errors and parameter errors respectively. The measurement redundancy ratio is 2.51. The standard to select the topology errors are that it cannot make the entire system unobservable, and the real power line flow is larger than 80 megawatt. For each type of bad data, the number of bad data we tested was from 10 to 500, and for each number we run SE Plus on 100 randomly selected bad data. The final results show that the bad data rejection rate is between 70% and 90%. It is also good to see that the bad data rejection rate of SE Plus is not sensitive to the number of bad data. We display the average voltage magnitudes for each type on different number of bad data. Because most of bad data were rejected, the average voltage magnitudes have relatively small changes from 1.015 to 1.019 per unit, which implies that SE Plus can keep the accuracy even under a large number of bad data. Furthermore, for all the massive testing cases, the convergence rate of SE Plus was 100%. For WLS-based state estimators, to detect and identify the bad data using residual analysis is the strategy. The scheme of WLS state estimators minimizes the residuals of bad data-related measurements, which cause the bad data detection extremely hard. It cannot reach a solution if the bad data are severe. It is not originally designed for the applications when bad measurements are inevitable, like power systems state estimation. For SE+, to reject the bad data-related measurements to enter the basis set, ZB, is the strategy. It is easier to effectively handle bad data than that of WLS state estimator. The influence of bad data on the solution is controlled and minimized. A more accurate solution is still able to be reached when bad data are present. SE Plus is not sensitive to all types of bad data. SE Plus is robust.